Here's another synthesis example, and this time we've made it kind of hard on ourselves because we have no functional groups in our product. So this is going to lead to our other strategy for synthesis, right? So what do we do? So I just got done telling you in the previous video about how identify the functional groups. They'll tell you what to do. Now we look at this. This is nothing but an alkane, right? So there's no functional groups to guide us in what we're doing. So that's a problem, right? But obviously we've changed the starting material into our product. And so what's happened between our starting material and our product, what we've done is we've added carbons. Now the question that you should probably be asking yourself is how many carbons have we added? Well, let's find out. So if we number these carbons, right, we have 5 carbons in our starting material, and it stands to reason, right, we have a CH3 over here. This is probably still going to be a CH3 in our product. So let's start there. This is carbon 1, and then 2, and then 3, and then 4, and then 5. So those 5 carbons, we can start with an assumption that those 5 carbons are going to line up with the 5 carbons that I just numbered. And so then we can count how many carbons we've added. So we have carbon 1, we have carbon 2, and then 3, 4, 5, 6, and 7. So we've added carbons, and specifically, we've added 7 of them, right? So it's reasonable to assume that all of these carbons are going to get added in a single step, right? If we can pull that off, that would be great. So we need a way to add these carbons together. So while the alkane is not a great functional group, the added carbons tells us something because so this is our clue, because we really have only talked about one reaction that leads to adding carbons, right? And that is the SN2 of a terminal alkyne conjugate base. Okay. So to do that, we need a terminal alkyne and we need a good leaving group, right? We need a primary leaving group. So we have 2 pieces of the molecule. We have this 5 carbon chain, we have this 7 carbon chain, right? We can assign these roles to those and say, all right, if we're going to make this happen, this is how we want to do it. And now we just have to figure out which way do we want to do this. Do we want to convert this alkene into a terminal alkyne, or do we want to convert this alkene into a primary leaving group? You can do either one, right? Both of them work. So you make your choice and figure out what reactions will lead to that, right? I'm going to choose to turn the 5 carbon chain into the terminal alkyne, right? So I'm going to choose to say this is my 5 carbons and this is my 7 carbons. But if you want a challenge, you should go flip those 2 around and see if you can do this synthesis that way. All right, so terminal alkyne with 5 carbons. There we go. That's easily enough done. And then I need my 7 carbon chain. And with a primary leaving group. Good? Hopefully that makes sense. Notice that I want my structures to look the same. So I'm still going to have my 5-membered ring with 2 carbons coming off the end, 5-membered ring, 2 carbons, and then I add my leaving group. Okay. Here's my terminal alkyne. All right, so once we do this, if we add these together and add a strong base, I'm going to use sodium hydride, right? We're going to make the conjugate base of the terminal alkyne. Well, let's do it. Why not? We got all the time in the world. Right, we're going to make the conjugate base of that terminal alkyne. And then that conjugate base is going to do the SN2 reaction to break that primary leaving group away. Now that's going to make something that almost but not quite looks like our product, right? Now we have our 12 carbons, right? We have 1, 2, 3, 4, 5, and we have 1, 2, 3, 4, 5, 6, 7, right? We have all 12 carbons in there, so that's good. Now we just need a way to get rid of these pi bonds in order to get to the product, right? And so we think back and we think about, okay, going from alkyne to alkane, that's hydrogenation. And so we can just do H2 and palladium and convert that. So if we can make this make this terminal alkyne, react it with this 7-carbon chain, make this and do hydrogenation, we can do that. So the only thing we have left to do is convert our alkene to our terminal alkyne. Right? So alkene to alkyne is another reaction sequence that we've covered. We brominate first, and then we eliminate. So just like we did on the previous slide, two equivalents, right? Alkene to alkyne is bromination followed by elimination. Then we do a substitution reaction to get all our carbons in place, and we do hydrogenation. So this is a 4-step sequence. We have bromination, elimination, SN2, and hydrogenation. Again, that's if you didn't see all of those in the same time frame that I saw them, that's okay. This is a little bit new, and we're still going to practice this a fair amount before we get to it. But the point here is counting carbons, right? So sometimes the functional group difference is not the presence of things like bromine or oxygen or anything else, right? Sometimes the functional group difference is I've got 7 more carbons than I started with. And that's always a clue, because how have we added carbons? We've really only done that one way, and that's the SN2 of a terminal alkyne conjugate base. So as soon as you see that you've added carbons, think about where you're adding those carbons and how can you change that into a terminal alkyne with a primary leaving group so that the SN2 reaction will give you all the carbons that you want. And then from there, then you could go forward to the product or backwards to the starting material, figure out all the reactions that you need, and you are set. All right, happy synthesizing. If you do flip them around and change the role of the 5-carbon and the 7-carbon fragment, I would love to see how you did it. All right, thanks, and see you again soon.